delighted to introduce our speaker today, Vinny. Vinny Mikuni is a machine learning postdoctoral fellow at Berkeley Lab and an incoming associate professor at the Kobayashi Maskawa Institute in Nagoya, Japan, where he is joining us today from. Vinny's research lies at the intersection of machine learning and fundamental science, where he develops algorithms to tackle core challenges in physics. His recent work includes fast simulation frameworks for fluid dynamics, collider physics, nuclear physics, and astrophysics using diffusion-based generative models, innovative methods for solving inverse problems in collider and neutrino physics, and leveraging pre-trained models to accelerate discoveries in particle physics. Vinny earned his PhD in 2021 from the University of Zurich, where he measured the production cross-section of top quark pairs in association with B quark and led searches for new physics and signatures involving third-generation fermions using CMS data. Today, Vinny is going to be giving us a talk titled Accelerating Discovery in Collider Physics with Foundational Models. So Vinny, without further ado, I am going to hand it over to you.
Yeah, that sounds great. And thank you very much for the introduction. I'm very excited to talk about this work that I've been doing the past couple months. And even more excited because today was also the day that the follow-up work that will be covered during this presentation was published on arXiv. So that would be the first time that I'll be able to talk about it. But let's start. And as there was already mentioned, the title of this talk will be Accelerating Discovery in Collider Physics using Foundational Models. So focus a little bit more in the collider physics side or the high energy physics side. And I think it would be great to first start by introducing what particle physics is really about. And the kind of physics that we are interested in understanding is the fundamental question about what the universe is made of. And one of the ways that you can try to tackle this very fundamental question about the universe is through particle interactions, is through particle collisions. Accelerators like the Large Hadron Collider, we accelerate particles near the speed of light and we smash them together. And the reason why we do that is because from one of the most well-known equations in the whole scientific world, set by Einstein, E equals mc squared, which means that if you have enough energy, we can create new particles, you can create things that we don't expect out of these particle interactions. By studying what we can produce through particle collisions, you can understand how does the fundamental building blocks of the universe behave. But of course, if you want to create an accelerator that can accelerate particles near the speed of light at very high energies, then you need very large experimental facilities. For instance, the Large Hadron Collider, which is located in this border between France and Switzerland, is a 3-mile accelerator facility that accelerates protons at these very high energies. And depending on the type of particle that you might be interested in studying, the probability of being able to produce them through particle interactions can change drastically. So in this plot here, what I'm showing in the x-axis corresponding to different types of particles that we want to study through particle interactions, while in the y-axis, I'm showing the cross-section, or roughly how likely it is for you to be able to produce these different types of particles. And as you can see here, depending on the type of particle they want to study, there is orders of magnitude of difference between what is most likely that you can produce through a particle interaction to the most rare processes that you might also want to study in order to understand how the universe behaves. To give you a little bit more of a context of how hard it can be to study some particles that can be very hard to produce, let's take, for instance, the Higgs boson particle. So this particle was first measured for the first time 10 years ago, even though the predictions for the existence of this elusive particle already existed for almost 50 years now. And the reason why it took us so long to be able to see those particles being produced through our experiments was because the probability of producing a Higgs boson at the Large Hadron Collider is of 1 in 10 billion. And this number is absurdly small. To give you a little bit more context, For instance, the odds of winning the lottery or the Powerball is about 1 in 200 million, while the odds of being killed by a vending machine is 1 in 100 million. Which means that if you're just interested in trying to produce 2 Higgs bosons in a row, that's already way less likely than you winning the Powerball and then being killed by a vending machine just after. Which means that the fact that we were able to observe not only a single Higgs boson being produced, but actually an excess, a bunch of collisions that were compatible with the production of a Higgs boson, which is this time peak that you see here on the left, was already a very hard task to accomplish. But the way that we are able to accumulate such a large data set is because we produce particle collisions at the Large Hadron Collider very, very frequently. Roughly every 25 nanoseconds, we are trying to smash protons together, and roughly that yields about 600 million particle collisions per second. Most of them that we can still save and try to use that for physics analysis in order to study what are coming from these particle interactions and to search for very interesting particles that we might be interested to study. Amongst those particles that we are going to study and the focus of this talk today, I'm going to talk about an object that we measure during our experiments that are called jets, where there's some particles that can interact with the strong force. These particles, when they do these interactions with the strong force, the way that we measure them through our detectors is not as a single particle hitting a part of my detector, but rather this particle produces a shower of additional particles from which those showers, they will be collimated and hit my detector and look like a spray of particles that we can measure. And that's the object that we call a jet. These jets, they are basically the most common objects that we can produce at the Large Hadron Collider coming from these particle interactions, but they're also very complicated because roughly, depending on the energy and the type of the particle that you're trying to study, the signature, these jets can contain tens to hundreds of additional particles that we need to measure very precisely with our detector. And of course, if you want to study what is the original particle that produced this jet, so try to identify what was this particle, then we need to use the full information that is measured by our detectors in order to assess what was going on before that. But if you want to use some machine learning algorithm that can understand this kind of structure, then we first need to think how we can represent this kind of particles, this kind of jets, in a way that we can use our algorithms. And this question has been addressed in many different directions by our high-energy physics community. One of them is inspired by large language models. Maybe we can represent these particles as tokens, where each particle and their information, which in this case can be the momenta of each of these objects plus additional information, can be tokenized in the same way that you do for a large language model. And then we can create our jets by using this tokenization strategy. However, a different way that is slightly more focused on how we normally already use these data sets is to, instead of using a tokenization or some discrete representation, is to use a point cloud representation, where in this case, the advantage is that we don't lose information by trying to tokenize continuous distributions like the energy of a particle that we measure in our detectors. And also we have some additional usefulness from this type of representation that I'm going to show a little bit later. Because when you actually look at particle interactions, the way that you really measure them is very similar to how point cloud processing already exists outside of high-energy physics. And a point cloud, if you're more familiar with 3D imaging, is basically a set of points without any specific order, so they are permutation variants. They are described in some metric space. It could be in the three-dimensional space, but in the space of our particle interactions, we can use different types of coordinates that highlight distances that are more relevant for the quantities that we want to measure. But otherwise, our particles also don't follow any specific ordering, and we just have this bunch of particles that we can use to try to understand what was going on. But if you're trying to represent our jets or the objects that we want to use for our analysis as a point cloud, then the second question on trying to create something that looks like a foundational model for high-energy physics and for fundamental science is to try to answer the question of what should we teach AI about particle interactions? How can we convey the very complicated structure of particle interactions to a machine learning model? And again, there are many different ways that people have been trying to tackle this issue. For instance, again, inspired by large language models, we can go in the unsupervised direction, where you can try to do something that is very similar to how, again, we train large language models using mask modeling. You can imagine that I can give you a set of particles, I can mask some of them, and I can pass through a model that tries to predict the properties of the particles that I masked. Similarly, you can do that not only by masking particles in the original representation space, but you can use something that's more similar to the JEPA direction, where instead of masking objects in the real space, you first encode them in some latent embedding, in some latent representation, from where you can then mask part of these contents and then ask your model to predict what you masked in the latent space. Another interesting direction that is also geared towards the unsupervised methods of pre-training foundation models is using generative models. You can imagine that by asking a model to be able to generate particle interactions, you are implicitly injecting the knowledge of how particle interactions should behave, how particles correlate against each other, to a specific machine learning model that can learn how to generate with high fidelity how these interactions look like. We can also have other options that are not necessarily completely unsupervised, but you can also do something that is semi-supervised, which is also a very popular direction of research in fundamental science, where you can use, for instance, contrastive learning or resimulation. You can imagine that I can have a data set with some very specific symmetry that I know it should be held by the data set that I'm working with. For instance, if I rotate, if my data set's the same, then I can use contrastive learning to create pairs from where I can tell my model that rotated versions of my original data set, they should represent the same objects, whereas something else needs to be pushed further apart. Similarly, in high-energy physics, we can have different types of simulators with different assumptions on how particle collisions should behave, but they are all trying to simulate the same physics process. And we can use the same strategy of contrastive learning by saying, well, I have two different physics simulators that try to represent the same object, so they should have similar representations. Whereas if I'm trying to do the representation of a different physics process, a different set of particles, those should not be very similar to the ones that I'm working with. However, another interesting direction that is a lot more unique to the fundamental sciences is trying to define a way to do a supervised strategy to train or pre-train a model. Of course, for large language models in general, having a supervised pre-training is basically possible since most of the data set has no labels. But in particle physics and also in many other fields in fundamental science, we have very good simulators that inject the knowledge that we currently have on how nature works at the level that we understand. And by using these very specific simulators, we can create simulations that already contain labels. I can tell you what kind of physics process I'm interested in, and I can simulate exactly that physics process within my simulation pipeline, which means that I have not only a very large data sets of data that has no labels that I measure with my experiments, but I also have access to very large simulation sets from where all of those data sets have labels that I can use, for instance, through a supervised strategy by just trying to classify different types of particle interactions. And the model that I'm going to talk about today, which is named OmniLearn, uses the idea that we can combine both unsupervised and supervised strategies in order to get most of the information from the data sets that we have available in high-energy physics in order to accomplish multiple downstream tasks afterwards. So the idea would be to combine an unsupervised method, which means generating particles, together with a supervised method, which means classifying different types of particles. And the idea is that if my model is able to do both tasks really well, being able to generate particle interactions and be able to know what are the differences between different types of particles that I'm creating, then this model will have a better understanding on how particles interact in the first place. But the other reason why I'm very excited to give this talk today is that this model, OmniLearn, that I worked with collaborators last year, has now been superseded by this new algorithm that we call OmniLearn, as very creative, as you can see, which was submitted to arXiv and appeared today. So that's really the first time that I'm talking about this model and sharing the findings that we got within this paper. So first, I want to go through the details on how we build this model. But first, starting from the general concepts. Again, we want to have a general model that is able to accomplish multiple tasks that are going to be relevant for some of the things that we want to do downstream. Again, classification and generation. But that means that for both of these tasks that we want to accomplish, they will share a embedding space that will be created using a combination of transformer layers and also graph neural networks. The idea is that graph neural networks, they are really good at learning the local information of my particle interactions, which can be really useful, whereas transformers, they are really nice at learning long-range interactions. And we can combine the two in order to get a global representation that is not only scalable to very large data sets that we want to use, but also can code the information in a more efficient way. But there is also another issue that we have to deal with. That is the fact that depending on the data sets or the simulations that you're going to work with, the information that you have available for each physics process can be quite different. For instance, there are some data sets where the information that we have available are only the properties of the particles that you measure, only their kinematic information. So you measure just the velocity of these particles, and that's it. However, there are some other data sets where not only you have the information of the kinematics of these particles, but also have some additional quantities. For instance, you can have some particle identification algorithm that runs over these objects and assigns a label to each of these particles. Say, oh, this one is an electron, this one is a pion, so on and so forth. But you can also have some other data sets that can even have more information than this. For instance, when charged particles are passing through the detector, they hit different parts of my detector, and that information could also be given to my model. But because not all data sets have all the information available, we need to figure out a way to train a model that can learn both a representation that knows when this information or this additional information is present or when it is not. The way that we do that is by basically applying something that is very similar to a dropout layer, where in the case of dropout, the model learns how to still use the information even when parts of the inputs are going to be dropped. And similarly here, we are going to train a model where additional information, they can also be randomly dropped during the pre-training phase, which means that the model learns how to embed that information both in the presence and in the absence of the additional information that I can use from these different data sets. From there is also some additional things that are very useful for this point cloud representation of particle interactions. For instance, we use class tokens. So if you're used to visual transformers, for instance, then you already know what I'm talking about. But basically, what we're going to do here is to create trainable tokens that are going to be combined with real particles in my point cloud and these trainable tokens that I use it to summarize the information of my point clouds, of my Parquet interactions. The reason why these class tokens, they are very useful for us is because Parquet interactions, they have different numbers of Parquets being produced, which is not a fixed number, which means that if you're just taking, for instance, the average of some representation, that can be a bit tricky because the number of Parquets can vary drastically, depends on the type of collisions you're looking. But if you train a model with the class tokens that can be used to summarize the point cloud in a learnable way, then it can better handle these particle multiplicities that we need to deal with. And in the way that we do that is that we have these trainable tokens that are combined with the real particles in the point cloud. When we want to do the classification of different types of particle interactions, then the output of the classifier comes directly from trainable layers that are looking only at these trainable tokens that we injected into the point cloud. So basically, the point cloud the trainable tokens summarize the point clouds, and from then we derive the classification labels. But in the case that we are trying to do the generation part, we are trying to generate part interactions, then we don't need these classification tokens. We just need the information coming from the rest of the point cloud so we can remove them. But talking about the generation, then we also need to define what kind of generative algorithm that we want to use in order to be able to generate particles. In this case, we are going to use diffusion generative models, which are basically the state of the art right now for generative tasks. And if you have seen images like that on the internet, and well, most of the images in the internet right now are generated by generative models. We can also create an algorithm that is very similar to what you see here. I give you a prompt, I can give an image. So for this image that I just generated from scientists at FirstPrinciples working in science and machine learning, you get this very nice picture. We can do something very similar. I can tell you what kind of Parquet interaction I want to generate from my model, and my model can generate that specific type of Parquet interaction. So the way that we're going to train the model is by combining in the loss function, the classification task, the generation task from the diffusion model, plus one additional term in the loss function that will align the representations that are used for both of these tasks that we want to accomplish. So this term that I'm talking about is the last term on the right, where we are going to try to also classify my point clouds. But instead of looking at the clean inputs that I use for my classifier, I'm going to use the inputs that are perturbed during the training of the diffusion model as an input to my classifier, and ask my classifier to try to predict what kind of Parquet interaction is it coming from, which means that the embedding space now will be aligned for both of these tasks, and we'll also improve the generalization capabilities of the model that we're going to see later. But before I start showing what we can do with this model, I'm going to quickly talk about the datasets that we cook up for these projects, where in the case of this OmniLearn model, the follow-up that just appeared on arXiv today, we are going to train a model using 1 billion jets, which is one of the largest datasets that are machine learning ready and very easy to use. From the software package that we also make available, you can access this entire dataset containing 210 different types of jets or classes that you can use for the classification. And they also have a mixture of both real data and simulations. Now, what can we use foundational models in high-energy physics for? If I take my OmniLearn model, if I train with 1 billion jets to perform classification generation, then what else? What can I do with it? Well, the first one that we wanted to investigate corresponds to doing a jet classification. One of the most common problems that we have to face in high-energy physics is the issue that if you're interested in some rare process that we want to measure, then we have a lot of background coming from other particle interactions that we don't care about, which means that we need to separate signal from background, a very standard task in machine learning. And we also have a very standard data sets that we use to benchmark the performance of many different algorithms since this data set was introduced a few years ago. And what we're going to do is that I can both train the model that I just proposed from scratch. I don't use any sort of pre-training, or instead I will take my pre-trained model and just fine-tune for these specific data sets, which is not part of any of the pre-training data sets that I used before. Instead of looking at that very complicated table, I can show you just a single plot where if you look at the publication year, so this data set was introduced around 2018. This metric here is the details, they are not that relevant, but basically the higher the better. And what you can see is that for many years now, people in our community, they have been developing different types of algorithms that have been pushing the performance of this benchmark further and further. And when we do our OmniLearn model that was pre-trained and then we fine-tune this data set, we obtain the highest level of performance compared to all the other benchmarks that were already proposed for this data set, which is pretty nice. But this data set, even though it's a traditional benchmark, so that's why we use it to showcase the results that we get, it's not very realistic. There are a lot of simplifying assumptions that were done in order to create the simulations for these data sets that do not make them very realistic when you actually want to use these kind of algorithms for a real physics analysis in a real experimental collaboration, the Large Hadron Collider. But this problem, then we can tackle by using a different data set that was made public just a few months ago, which comes from the Atlas collaboration, which is one of the main experimental facilities within the Large Hadron Collider, where they made available their own private simulations that use it for real physics analysis that we can use in order to train a similarly classifier that can try to distinguish different types of particles. In this case, that's basically the most realistic kind of simulations that we can have to really probe how well these algorithms can work in a more realistic scenario. And from the table on the left, as you can already see, the OmniLearn will also do really well. But I can also, again, show you a little bit, some more colorful plots. For instance, GN2 is the current algorithm that is used by the Atlas collaboration. So that's our baseline that you're trying to beat, basically. And this data set that they made available publicly is not that small. It's already 168 million jets. So this is a very large data set. But what we observe is that even when we fine-tune our models on these still somewhat large data sets, we still observe benefits from having a model that was fine-tuned and pre-trained it with 1 billion data sets versus a model that was trained from scratch. And what you can see in these plots, in the y-axis is something that is, again, very similar to the metric that was shown before, but in this case corresponds to the false positive or 1 over false positive versus the signal efficiency, the true positive in the x-axis. The different ratio plots, they correspond to taking different classes of particles as my background that I want to reject while keeping the signal particle fixed. And in the ratio, I'm showing the performance that we obtain divided by what you observe from this GN2 algorithm, which means that anything above 1 means that we're doing better than GN2. And for all these ratio plots, as you can see here, we do sometimes even way better than what is the current state of the art from this collaboration, even improving by a factor of 2 how much you can reject background while keeping the same true positive. But let me talk about a less straightforward application that corresponds to anomaly detection. So far, I've been talking about simple classification of signal versus background, something that is very important for us in high-energy physics. However, That's still a very straightforward application for model. But there is a less straightforward application of machine learning and physics, which corresponds to also one of the goals as to why we keep studying particle physics in the first place. There are still a number of open questions about things in the universe that we don't understand. For instance, there are several hints that something that we call dark matter exists, even though we don't know what it is. But if it is a particle, then maybe it's something that can be produced at the Large Hadron Collider through particle interactions if we have enough energy. But the challenge here is that we don't know what we are actually looking for. So it's very similar to what if I were to ask you the question on how to find a needle in a haystack of particle interactions. But this question is actually very easy. You just need to use a magnet and you can find the needle very quickly. It doesn't matter how big is your haystack, you can still find it. And this allegory is actually very similar to how we've been trying to search for new physics or new particle interactions at the Large Hadron Collider in the past 10 years. First, we start from some plausible theory that can explain, for instance, the existence of dark matter in the universe. From this new theory about nature, we try to verify if that theory is correct using the data that we measure from our experiments. If we do find that our measurements are compatible with the predictions of this new theory, then that's amazing. That means that we found something that we didn't understand about nature, might get a Nobel Prize, call it a day, and that's it. Otherwise, if we don't find anything that matches the predictions of this new theory, then we still learn something about nature. We learn about what it cannot be, or by placing constraints on the parameters of this theory that cannot be correct because the data does not agree with these predictions. And in the past 10 years, that's how we've been mostly doing this kind of searches for new particle interactions. In the plots that I'm showing here, each line corresponds to a different type of model that predicts the existence of some new particles that in principle we could measure. We didn't find anything, which means that we place constraints on how massive these particles they can be. And as you can see here, from each of these lines, that corresponds to roughly a PhD, 4 years of a PhD student working full-time in order to be able to do these searches for new interactions. And because we've been doing that for about 10 years now, we have hundreds of these results where, unfortunately, we have not yet found any hints as to what new physics should look like. But at least we have a good way of limiting a number of these parameters of this theory. But perhaps there is a more interesting way to try to search for new interactions, even if you don't know what you're looking for. And that's where anomaly detection enters. Instead of starting from the magnets that tries to find for a search for a specific needle in my haystack, I can go directly to the haystack and ask what is not what is not compatible with how I describe my theory of particle interactions. Because if I'm able to find an anomaly, something that does not match my expectation of particle interactions, then I can try to interpret why that does not match my expectations, and that might lead to a possible new physics scenario. And otherwise, if I don't find anything that is weird, if I don't find any anomalies, then I'm able to constrain many possible theories in one go without having to maximize for some specific theory scenario. So the general approach that we're going to take for this kind of problem is that we need to accomplish two different goals. First, we need to estimate how the data should look like if the data follows the hypothesis that corresponds to standard particle interactions. There's no new physics. That's how we model, how we understand particle interactions right now, how the data should look like if that's the case. And from these predictions, so these orange bands here in this histogram, I have to compare with what I actually measure from a data set. And if I see any differences between what I'm measuring and what I'm predicting, then there might be a hint that something is going on. And even more exciting, if we use machine learning, we do not need to restrict ourselves in looking at one-dimensional observables, or one-dimensional marginals of this high-dimensional particle collision space, but instead we can search for things that are anomalous in high dimensions with weird correlations. One very traditional way of doing these two steps of predicting how the data should look like without new physics and doing the comparison of the data is something that we call bump hunts. So I showed some plots before that had this Higgs discovery, where we saw this tiny bump corresponding to the Higgs boson being produced. And that's because if you look at a plot that looks at the number of particles versus the mass, for instance, and you make it a histogram, then if you produce a new particle, the new particle has some fixed mass, you have some localized resonance, which means that what we can do is simply to define a signal region, which is a range in this mass interval, and sidebands, things that are outside of the region of interest, where the idea is that we can determine how the background looks like for these sidebands where new physics is not located, and then interpolate in the region of interest in the signal region to predict how the background should look like. And from these predictions, we compare against the data, see if they are compatible with each other. If they are, then we don't see anything. But if they are not, then there might be a hint of new physics. But again, by using machine learning, we can do that in high dimensions. We don't need to only look at the mass as one single observable, but rather what we can do is to train a generative model that looks at the sidebands, look at the regions where there shouldn't be anything exciting, and interpolate the generative model to generate background predictions in the signal region. Now that we can generate background predictions in the region of interest, we can train a classifier between the data that we actually measure and the predictions of my backgrounds. And if this classifier picks up anything unusual, then there might be a hint of new physics. But again, we need to have a generative model and a classifier, so things that are exactly built within OmniLearn. So what we're going to do is that we take really experimental data. We are not going to use any sort of simulations here. We're going to take data that was measured at the Large Hadron Collider, and we are going to do that. We are going to train a model that will try to generate the backgrounds using sidebands, and then do the interpolation, and then train a classifier. So what you're going to see here on the left are the results that we obtain. If I don't do any fine-tuning, I just train my model from scratch. Now I'm trying to search for a signal that I know that it exists. So this is not new physics that I'm trying to search. I'm just trying to probe if my method works for a particle that are called top quarks that I know exists and are produced at the Large Hadron Collider. The tricky part is that compared to the amounts of background that we have, top quarks are only 0.1% of the data. So there is only a very tiny fraction of these objects, which means that we need to do the background interpolation really well, otherwise the classifier won't be able to pick it up. And that's exactly what we observe. If I place tighter and tighter cuts on the outputs of this classifier to only look at events that are more anomalous, as given by my classifier outputs, what I see is that from this model that was trained from scratch without any fine-tuning, I don't find any new physics or any sign of particles that I already know they should exist. On the other hand, if I take my OmniLearn model, which was pre-trained, and then I fine-tune my classifier on these data sets, what I observe is that when I train this classifier and apply tighter and tighter cuts on the outputs of this classifier response, I start seeing this tiny bump appearing on top of my background prediction, which is compatible with this particle that I'm talking about, compatible with the top quarks. Another very exciting thing is that, well, I'm talking about having this pre-trained model, but another thing that we observe is that the size of the pre-trained model also matters. If I use a bigger model, so in this case about 50 million parameters versus 3 million from the previous plots, on the left, if I train from scratch, I still don't see anything. But now the peak that I observe, or this excess of events that I get from my model that's being fine-tuned, this data set is much bigger, which means that this model is even more sensitive to these new particle interactions. Another thing that we can also do that is alternative to this strategy that I just described is to simply take the pre-trained model, don't do any fine-tuning. Because I have 210 classes that I mentioned before, let's just try to get classes from the outputs of this model that are more or less compatible with things that are weird. Just take the classes that don't look like the most classes that I have in my background and use that to try to tag what is an anomaly and what is not. In this case, there's no fine tuning. I don't need to train anything. I just take my OmniLearn model and apply directly to the data. And what we observe is that, again, bigger models, they outperform smaller models, but in both cases, we find new physics, or in this case, top quarks. And in both cases, we find with better sensitivity, or they're more sensitive to this signal than our previous strategy. So that's basically it for today. Today, I tried to introduce the idea of foundational models that we use here to really understand the data. So instead of focusing on the language direction, we're really trying to learn a useful representation of the data sets that we collect through particle interactions in a way that when we do the fine-tuning of these models, we might be able to achieve performances that were not able to be achievable from models that were trained from scratch. Otherwise, we also have some applications that can be quite exciting on using these foundational models without any fine-tuning whatsoever, just asking the right question, quote unquote, so looking at the right outputs of the model, we can already use them to find things that are way exciting and things that can be useful for our physics analysis. Even though I focus on two applications, focusing on classification and the generation using user for anomaly detection, there are also a number of other applications that we already explored in the past, and we can also explore with our new model on fast survey models for simulation, physics simulation in Greenwich physics, or calibration of our data sets to make them more realistic. But otherwise, if you're interested in trying for yourself and having access to these very large data sets, the software package containing also all the pre-trained models and checkpoints, they are available from this GitHub link. And if you want to take a look at the paper itself, then it's now on archive, and you can also access from this link on this slide. Thank you very much, and let me know if you have questions.